Okay, now let's talk about satellite motion in a circular orbit. Okay, the satellite motion in a circular orbit. So, in satellite motion, we will learn two things. One is the velocity of satellite, the velocity, how fast the satellite revolves around the Earth. Okay, another one is the period of satellite. How long does it take for a satellite to complete one revolution around the Earth? That is period. How long it takes to complete one circle around the Earth? That is period. So how to calculate the velocity of the satellite, how fast it revolves around the Earth, and how long? We want to know two things: how fast and how long. Okay, how fast and how long. Okay, how fast and how long. Sorry, how fast and how long. How fast and how long it takes to revolve around the Earth. Okay, so how to calculate? We use the one concept from the chapter circular motion. We use the concept from the chapter circular motion. So in circular motion, when any objects make a circular motion, it must have centripetal force. Because the centripetal force will continuously change direction of velocity of the object, so that the object will move in a circle around the center. Okay, so it needs centripetal force to keep the object to move in a circle, or to move in a circular motion. It needs centripetal force. So for a satellite revolving around the Earth, it is actually depending on the gravitational force to provide the centripetal force for the satellite in order to move in the circle, to move in the orbit. We call it the orbit, okay, or the pathway for the satellite to revolve around the Earth. Okay, so what is the force that provide the necessary centripetal force for the satellite in order to move in the orbit? It is the gravitational force, or we can say the attractive force from the Earth. Okay, so it is the gravitational force from the Earth that provide the centripetal force for the satellite, so that the satellite can move in a circle. Okay, this centripetal force or gravitational force continuously change the direction of the velocity so that it move in a circle. You can see the velocity always change direction. You see, velocity is this way at this moment. Over here is to the right, to the left, to here, and then here downward, here to the right, here, and then here go upward. You see that the velocity continuously change direction, all because of centripetal force. So centripetal force always helps to change the direction. Always help to change the direction of what? Of the velocity. Understand? It always help to change it. So this centripetal force, this centripetal force is provided by the hold on a second. This centripetal force provided by the gravitational force always change the direction of this velocity, so that this satellite will always move in a circle around the Earth. Okay, so by using this concept from the chapter circular motion, the gravitational force equal to the centripetal force, Fg equal to Fc. You see that? Fg equal to Fc. Fg equal to Fc. Okay. And then here also the same. Yeah. Here also the same. Hold a second. See, both the equation for velocity of satellite and period of satellite, we use the same formula, same concept, Fg equal to Fc, to derive the final formula for velocity and period of satellite. Okay. So Fg equal to Fc, gravitational force equal to centripetal force. So first we look at velocity of satellite. So Fg equal to Fc. Fg is gravitational force, is gmm over r squared that we have learned earlier. Okay. Take the two masses. One is the mass of Earth and another one is the mass of satellite. The big M is the mass of Earth, or the point mass. The small m is the test mass, or you can say the satellite mass of satellite. Okay, gmm over r squared. And then centripetal force, the formula is mv squared over r. We learned in chapter circular motion. Okay, mv squared over r. This m here is the mass of satellite. Look at what happened to the mass of satellite. The test mass or mass of satellite is being cancelled in the equation. You see, being cancelled off. So this equation has no more the mass of satellite, is already being cancelled. Okay, so after that, we rearrange the formula. We finally will get this formula. Velocity of satellite v equal to square root gm over r. The m on top here is the mass of Earth, or the point mass, the big M, the mass of Earth. What is point mass? He is the, again I want to say, he is the provider. Yeah, why we say is point mass? Point mass means the provider of the gravitational provider of gravitational field. Gravitational field. Yeah, he is the provider, the point mass. Okay, so it is the Earth who provide the gravitational field around it, so that for the satellite to have the gravitational force. Because why satellite has this gravitational force? Why he experienced this gravitational force? Because it is inside the gravitational field of Earth. Understand or not? So what is actually gravitational field again? It is an area where you can experience the gravitational force. Look back to the definition of gravitational field strength. Gravitational field strength, the gravitational field is the area where you can experience the gravitational force. The definition for gravitational field is gravitational force per unit mass. Gravitational field is the area where you can feel this gravitational force. Okay, you can feel this gravitational force. So go back to the last one. Yeah, so why this satellite has experienced this gravitational force? Because it is inside the gravitational field of Earth. Okay, gravitational field is the area where you can experience the gravitational force, the gravitational pull. Okay, that's why we have gravitational force to function as the centripetal force for the satellite to revolve around the Earth. Okay, so this mass is the point mass, or the provider of the gravitational field. We take the mass of Earth. Understand? And how about the R below here? R below here is the radius of the orbit. I just want to clean up. Okay, this radius, this R is this one. You see that? This R. The same thing as we learned in the gravitational field strength. The R over here, it is the same R over here. It's the same R with this one. The AGMM over R square is the same R with this one, which is radius of Earth plus the altitude h. So R is actually radius of Earth plus h. Okay, so same thing goes for this one. So the radius of orbit yeah, orbit for the satellite radius, because we know that this orbit and the Earth, they are concentric. Concentric. You know what is concentric? That means they share the same center. The center of the orbit is the same center as the Earth. They are concentric. They share the same center. Share the same center. Okay. Share the same center with the Earth. So the radius of the orbit is actually the center of the orbit is actually the center of Earth also. So that's why the R here, the radius of the orbit is radius of Earth. Yeah, the distance from the center to the surface of Earth plus the height of the satellite. That means distance from the surface, h. So R is actually radius of Earth plus h. Okay. So I want you to compare between this velocity of satellite with escape velocity, because both of them have almost similar formula. Do you notice that? This is velocity of satellite. This is escape velocity. Two different meaning. Okay, what's the difference between velocity and hold on a second. Make it nearer. Okay, just want to compare for you and see. Yeah, what's the difference between escape velocity? What's the difference between velocity of satellite and the escape velocity? Velocity of satellite is the speed of the satellite to revolve around the Earth. The formula is v equal to square root gm over r. However, escape velocity is the minimum. Just want to put the word minimum here. It's the minimum velocity required in order to escape completely from gravitational force of the Earth. That means from the surface, to jump from the surface to potential energy 0. Yeah, the minimum velocity for the, let's say for the Superman or the rocket, minimum velocity of the Superman or the rocket to jump from the surface to the potential energy equal to 0 joule, free from gravitational force, or to jump to the area where you have no more gravitational force, free from gravitational force. That's escape velocity. The formula for escape velocity is escape velocity is equal to square root 2 gm over re. You see, you have extra 2 here. You know, in the final exam, he will give you both formula. He will give you both of this formula. Okay. However, make sure you don't mix up these two concepts. This velocity is velocity for satellite without the multiply 2. Yeah, without multiply 2. That's for velocity of satellite. But the one multiply 2 is escape velocity. So don't use wrongly the equations. Yeah. Another difference is this one. This one is the radius of orbit. This one is radius of Earth. Okay. This one is the orbit. Yeah. Is the orbit. Is the radius of the orbit. That means you need to plus h. Okay. The distance here you need to plus h. The radius of Earth plus h. But the r here is just the radius of Earth. It's just the radius of Earth. No plus h, because it's escape from the surface. Because this one it escaped from the surface. This satellite is not on the surface. This satellite is not on the surface. It is at the orbit far away from the surface. Okay, far away from the surface. So that's why you have plus h over here. This one is radius of Earth plus h for the satellite. For the escape velocity, it is just the radius of Earth, because you escape from the surface of Earth, from the surface. That's the difference. Yeah, I just want to tell you. Formula is almost the same. This one square root gm over r. This one also square root 2 gm over r. Okay? Now good. Now let's go back to this one. Yeah, I just want to tell you that this mass over here is the mass of Earth. Yeah, this mass of Earth is not the mass of satellite. It's not the mass of satellite. So some students will ask me to compare. Let's say now you have a small satellite. Let's say I have a small satellite. This is just a small satellite. This one is just a small satellite. But now I have a gigantor satellite. Yeah, gigantor satellite with a bigger mass. With a bigger mass. The test mass is bigger. This one test mass is smaller. I have a giant. If not big enough, I make it bigger. Okay. Now my question is, which one will have higher velocity? Which one will have higher velocity? Is the giant satellite move faster? No. Is the giant satellite move slower compared to the small one can move faster? Which one will have higher velocity? The small satellite or the bigger satellite? Maybe some of you will say, oh, the small satellite easier to move, so it will move faster. It will move faster compared to the big one. Yeah. Small one easier to manual. Yeah. Manual. So it should move faster compared to the big one. Look at the formula. Look at the formula before you answer. You look at here. Velocity of satellite only depend on what? Only depend on the point mass. Only depend on point mass. Only depend on point mass. You see that? Mass of Earth. So it's independent of the test mass. The test mass is already being cancelled. Test mass is already being cancelled. So if you use a bigger satellite, okay, bigger satellite, the test mass is not inside the equation of the velocity. So a bigger satellite will have same velocity compared to the small satellite. They will have the same velocity because I can say like this. I written here. Okay. So velocity of satellite. Yeah. You look at the equation. It is independent of the test mass, independent of the mass of satellite. Okay. No matter big or small. Both big or small satellite will have the same velocity, same v, at the same distance from the Earth, at the same r. Okay, so they will have the same velocity. Okay, same velocity because the formula doesn't have the symbol mass of satellite, because the mass of satellite is already being cancelled before we get this equation. It's already being cancelled when we want to build this equation. The mass of satellite is already being cancelled. So the velocity of satellite just depend on the mass of the Earth, or the point mass. The velocity of satellite just depend on the point mass and just depend on the distance from the center of the orbit, or the radius of the orbit. Okay, it just depends on these two factors. This velocity of satellite does not depend on mass of satellite. Does not depend on mass of satellite. It's already been cancelled when we build this equation. Okay, so both big or small satellite will have the same velocity at the. Okay, so we can say any. One thing we can say is any satellite. Maybe this satellite is from Malaysia. Okay. Maybe this is our Astro. This is our Astro. Okay, from Malaysia. This one, maybe this one is I don't know what. It's from China. Satellite from the China. China satellite is bigger than our Astro satellite. Okay, so which satellite will travel faster in the orbit? Which satellite will travel faster in the orbit? Is it our Malaysia Astro or China? Again, because if both satellite at the same radius of orbit, in the same, or we can say if they are at the same distance, or we can say at the same orbit, or at the same orbit. If both satellite at the same orbit, or same r, or same h, okay, same distance from the center of the orbit or center of Earth, these two satellites will have same velocity. No, different. So different satellite at the same orbit will have same speed. Remember, we have same speed. Hear me again. Different satellite at the same orbit will have the same velocity. They travel at the same speed around the orbit. Travel at the same speed. Okay, because they are independent of the mass of satellite. It's already been cancelled in the equations. Okay, you see here, there is no mass of satellite here. What's left is just the mass of Earth and the radius of orbit. There's no mass of satellite here. Okay, enough. So now let's go on to the period of satellite. Period of satellite also how long? How long the satellite move around the Earth? We also use the concept centripetal force. The gravitational force equal to centripetal force because it's the gravitational force that provide the centripetal force for the satellite to revolve around the Earth. Okay, so again, gravitational force is gmm over r square. Centripetal force is mr omega square. Last time we used for velocity of satellite, we use mv square over r. This time for period, for centripetal force, we use equation mr omega square. Because centripetal force has several equations, can be mv square over r or mr omega square. But this time we put mr omega square because this mr omega square has this omega. Here we have omega. Omega here can change to period. Because what we want to find is period. Okay, so that's why we use omega instead of v. V don't have the period. You can also find period from v, but harder. This one is more direct. You have omega. Omega is 2 pi over period, so you can substitute omega with 2 pi over period. 2 pi f or 2 pi over period. F is 1 over period. Okay, so you can substitute omega with 2 pi over period into it, and then you can derive the formula. You get the formula for period of satellite, which is equal to 2 pi square root r cubed over gm. Again, here, the mass here is the mass of Earth. Is the point mass. Again, this one is the mass of Earth, the point mass. And this is the radius of the orbit. Radius of the orbit, so is radius of Earth plus the altitude. It's not just like the escape velocity, just the radius of Earth. No, you must include the h because again this one refer to the satellite. This r here refer to the satellite. How far the satellite from the center of Earth is the radius of Earth plus the h. Okay, so this r over here is the same as r over here, and mass of Earth here is the same as mass of Earth here, the point mass. Again, the period is also independent. So I can say here I also can add period. Here the period of satellite is independent of test mass. Mass of both big or small satellite will have the same velocity or the same period, or we can say same period. Okay, at the same distance from the Earth. Okay, the period of satellite is independent of the test mass or mass of satellite. Both big or small satellite will have the same velocity or the same period at the same distance from the Earth. If both satellites are at the same orbit. Okay, so we can imagine all kinds of satellites here. All kinds of satellite here, big or small, all have the same speed. All have the same speed, same period. All have the same speed, same period. Understand? Because they are at the same orbit. Same orbit and the same Earth. They revolve around the same Earth. Same mass, same point mass. And then they revolve around the same orbit, same r, same radius of orbit, same h. Okay, so they have the same period, have the same velocity for all. Okay, so that's the formula for velocity of satellite and period of satellite. Okay, v equal to square root gm over r and period equal to 2 pi square root r cubed over gm. So I hope that you enjoy this, and now we will move on to the next video. okay, for problem solving.